Hello everybody, my name is Philip Johnson and today I will discuss the third experiment for our physics course. This experiment involves using observation of motion of a star to determine the mass of an entity applying gravitational force to it, in this case, a black hole. The point of the experiment is largely to show that one can solve real-world physics problems through data collection and application of fundamental physics principles. The fundamental physics principles we will specifically apply in our model for this experiment are Newton's second law, aka the momentum principle, for this course, in which we're saying they're equivalent, and Newton's law of universal gravitation. Our general result was that we found the black hole in our model to be really big, nearly 24 times the size of the Sun in our solar system. The main physics principles we are going to use in our computational model, which essentially will crunch all the numbers and conduct the physics for this experiment, are the momentum principle and Newton's law of universal gravitation. The momentum principle states that momentum of a system is mass times velocity. To put it in an iterative prediction form, this turns to final momentum equals initial momentum plus Fnet times change in time. Perhaps most importantly, the law states that Fnet equals the change in momentum over change in time. This relationship between momentum, which involves motion, and Fnet, which involves force, which causes motion, is the key here. We will also use Newton's law of universal gravitation to find the black hole's mass. This law states that there is an attractive force between all objects in the universe. Since we're operating in space, this will be the only force operating in our experiment. This attraction can be calculated via the equation shown here, where g is the gravitational constant, with the value shown here. Keep in mind that this is more or less how a real scientist would approximate celestial body size in space. We're using these basic equations that can be taught in a Physics 1 course to simulate what a real scientist would do to solve a problem. That's pretty cool. It's important to know the initial data for our model. The following was provided in the prompt for the lab. Important things to note are the time, which is going to be about 1 day. That's how long our observed motion will be. And we have a stardata.csv file, which has position data from which we'll derive velocities, from which we'll derive momentum, which will derive Fnet. The positions are key. This data in mind, we edited the computational model to suit our needs. Instead of showing all the code together, I'll just show the important lines in slides after this. As in past labs, we have a while loop doing motion prediction using the momentum principle. The difference between this lab and past labs is that the positions are hard-coded. The positions that we'll actually see in the model when I run the code are from the CSV file. They have nothing to do with our prediction. We still have to predict, though, in order to calculate the mass of the black hole each step. You might be wondering why we need to calculate the mass of the black hole each time. The mass of the black hole is not changing, right? That's right, the mass of the black hole probably would not actually be changing. However, in our prediction loop using the momentum principle, we're deriving from the positions inside of the CSV file a different Fnet. As a result, we're getting a different result for the black hole mass, which will average at the end. Now let's get to the good stuff, how we change the computational model to actually perform the experiment. Step 1 is we find the initial and final velocities between 2 points given in the spreadsheet. xvel and yvel are just arrays filled with position data from the CSV. We can use positions to find velocities, and that's what we do here. Step 2 is compute the initial and final momentum from the velocities and the mass provided in the initial condition. Step 3 will be to find the change of velocity and change of momentum, then dp dt. Delta V is simply shown here, delta P simply shown here, and dp dt is just these two things divided. Note that Fnet is equal to dp dt. That's very important. Step 4 will be to break into parallel and perpendicular components. P hat is the direction of motion, d mag pdt is the magnitude of dp dt, and dp dt parallel then is equal to that magnitude times p hat. Final code changes are shown here. Step 5 is to break into the perpendicular component, which we can simply get from subtracting dp dt parallel from dp dt. Step 6 is to remember that Fnet equals dp dt, and the corresponding parallel and perpendicular components of Fnet are equal to the corresponding components in dp dt. The final step is to actually calculate the black hole each time. Here's how it would be represented in the code. I'm about to show the motion, but here's some upkeep that we need to look at. That for the arrows, Fnet is yellow, Fnet perpendicular is blue, and Fnet parallel is red. Arrow scale had to be fiddled with to make the Python model actually look good. In any case, let's look at this motion. Here's the motion we observed. The arrows here are scaled to their magnitudes. Note how they grow larger when they come close to the black hole, a product of Newton's law of universal gravitation. Let's get to our results. Calculating the mass of the black hole each step, we found it to be an extremely large number, almost 24 times the size of our sun. Remember, how he did it was using the momentum principle and Newton's law of universal gravitation inside of a computational model. Let's quickly answer some discussion questions. What's the difference between dPdt and FNet? After all, their parallel components and perpendicular components are equal. It all looks equal, so what's the distinction? The key difference is that dPdt describes motion. FNet is the reason for the motion we're describing. FNet is found by calculating the forces acting on the object. dPdt is found by observing motion, particularly attaining change of velocity over time. We can use positions like we did in this experiment to find dPdt. FNet is the reasons for the movement. dPdt is the results of the forces. We use FNet equals dPdt to approximate FNet for sufficiently small t, but conceptually they're not the same. The answer to the second question is simply no. Recall that to calculate the black hole mass, we manipulated Newton's law of universal gravitation in this form. With the same motion, r would not change. The star's mass would be the same, and the FNets calculated are derived from the position theta, which would be kept the same. Therefore, we get the same black hole mass calculations found in this experiment. Our answers are unique. This concludes my Lab 3 video. Thanks for watching.